Okay, for the first question, this is a picture of the shape. Kind of looks like a chimney that keeps getting narrower and narrower as it goes up. There is a cylinder, radius 4, at the bottom. Goes from z is equal to -1 to z is equal to +1. Sitting on top of it is a cone that sits right on top of it. The bottom of the cone's got a radius the same as that cylinder of 4. The top of that cone's got a radius of 2. Sitting on top of the cone is a cylinder, radius 2. And sitting on top of the cylinder is a hemisphere, radius 2. So there aren't any holes in this surface. So the question is, what is the flux of the curl of the vector field over that surface? And we can do this with great simplicity using Stokes' theorem. Stokes says, and here's the math, Stokes says that you can relate a surface integral to the curl of a vector field to a line integral of a vector field along the boundary curve of the surface. So this complicated looking surface really boils down to a circle, radius 4, parallel to the xy plane, cutting the z-axis at z is equal to -1. So R of t is, it's a circle, radius 4, 4 sine t, 4 cosine t, -1. R prime of t is the derivatives of those components. Notice that the z component is 0. So the line integral is simply f of r of t dotted with r prime of t from 0 to 2 pi. And remember, that z component, r prime of t, is equal to 0. So the z component of that gosh awful vector field kind of disappears. So we've got f of r of t dotted with r prime of t, which is -4 sine t, 4 cosine t, and then the z component, which we don't care about, dotted with -4 sine t, 4 cosine t, and 0, which is 16 sine squared t plus 16 cosine squared t, which is 1 times 16. So that line integral boils down to 16 dt from 0 to 2 pi, which is 32 pi. And that's how you compute the flux of the curl of the vector field over that ugly expression. Thank you.